Look at the primes: 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. Take any odd prime and divide it by 4. The remainder is always one of two things, either 1 or 3. It can't be 0 because then the prime would be divisible by 4. It can't be 2 because then it would be even. So every odd prime gets sorted into one of two camps. The ones that leave remainder 1, 5, 13, 17, 29, 37, 41. We'll call these the 1 mod 4 primes. The ones that leave remainder 3, 7, 11, 19, 23, 31, 43. We'll call these the 3 mod 4 primes. Two teams. Both teams get to grow forever because there are infinitely many primes. The question is, do they grow at the same rate? Intuitively, yes. Primes feel scattered, random. If you flipped a coin to assign each new prime to a team, you'd expect the two counts to bob up and down, sometimes one ahead, sometimes the other, with the lead alternating roughly evenly forever. That's the prediction, and the math, when you push it far enough, eventually agrees with that prediction. The prime number theorem for arithmetic progressions, proved in 1896, says the two counts grow asymptotically equally. The ratio approaches 1 in the limit. So if you plot the running count of 3 mod 4 primes against the running count of 1 mod 4 primes, you should see a fair race. Some leads, some falls behind. Total tie in the long run. What actually happens is not that. Start counting. Up to 100, how many primes are in each class? 1 mod 4 primes up to 100. 5, 13, 17, 29, 37, 41, 53, 61, 73, 89, 97. 11 primes. 3 mod 4 primes up to 100. 3, 7, 11, 19, 23, 31, 43, 47, 59, 67, 71, 79, 83, 13 primes. 3 mod 4 leads, 11 to 13. A small gap? Could be noise. Keep counting. Up to 1000. 1 mod 4, 80 primes. 3 mod 4, 87 primes. 3 mod 4 still leads. Up to 10,000. 1 mod 4, 609 primes. 3 mod 4, 619. Still ahead. Up to 100,000. The lead is now 34. Still in favor of 3 mod 4. Up to 1,000,000. Lead grows again. 3 mod 4 ahead by 60. You'd expect the lead to wobble. Two random walkers shouldn't have one persistently ahead. By a coin flipping argument, after 1,000,000 coin flips, the lead should bob around like the square root of the count, sometimes plus, sometimes minus. But it's not bobbing. The 3 mod 4 count is ahead at every checkpoint. Always. At 1,000,000, 2,000,000, 10,000,000, 100,000,000. 3 mod 4 leads. Something is wrong with the random walker model. You might think, surely the bias breaks at scale. Push to 1,000,000,000, 1,000,000,000,000. The error must average out. It doesn't. Modern computations push the comparison out to numbers with hundreds of digits. The 3 mod 4 count consistently leads the 1 mod 4 count over the vast majority of values. There are exceptions, windows where the 1 mod 4 primes briefly catch up, but the exceptions are rare, and the lead reasserts itself. So you have a counterintuitive situation. The theoretical prediction says, equal in the limit. The actual data says, persistent lead for 3 mod 4. Both are true at the same time. How? Because equal in the limit and 1 always ahead are not contradictory. The asymptotic ratio of the two counts is 1. The difference of the two counts can still be positive on average, as long as the positive difference is dwarfed by the total count. The ratio still approaches 1. Numerically, at x equals 1 trillion, the count of primes in each class is around 18 billion. The lead of 3 mod 4 over 1 mod 4 is on the order of a few 100,000, tiny relative to 18 billion, but always positive. This isn't noise, this is structure. Something in the way primes distribute among residue classes is forcing the 3 mod 4 side ahead. The phenomenon is not unique to mod 4. Look at primes modulo 3. Every prime other than 3 itself is either 1 mod 3 or 2 mod 3. Count them. The 2 mod 3 class leads, persistently, across every checkpoint you can compute. Look at primes by last digit. Every prime greater than 5 ends in 1, 3, 7, or 9. By Dirichlet's theorem, these 4 classes are equally populated asymptotically. By actual count, the primes ending in 3 and 7 persistently outnumber the primes ending in 1 and 9. The pattern repeats for every modulus. Some residue classes win, other residue classes lose. The race is rigged in some specific structural way, and the same way every time. The question of the video is, why? And the answer is going to wait. The first person to observe this pattern was a Russian mathematician, Pafnuty Chebyshev. The year was 1853. Chebyshev was 42 years old, already known for foundational work on the distribution of primes. He had proved Bertrand's postulate that there's always a prime between n and 2n, 5 years earlier in 1848. In a letter written to the German mathematician Hermann Fuss in St. Petersburg, Chebyshev observed the imbalance. He counted primes up to various bounds, sorted by residue, and noticed the persistent lead of the 3 mod 4 class. The letter was published the following year in the Bulletin of the St. Petersburg Academy of Sciences. Chebyshev went further than just observing the pattern. He stated a conjecture that the lead of 3 mod 4 over 1 mod 4 is permanent. For every x larger than some small threshold, he conjectured, the count of 3 mod 4 primes is greater than or equal to the count of 1 mod 4 primes. Always. No exceptions. This is a strong claim. It says, not only does 3 mod 4 lead on average, it never loses, ever, period. Once it gets ahead, it never falls behind. For the next century, mathematicians tried to either prove or disprove Chebyshev's conjecture. They counted further. The numerical evidence supported it. The lead kept holding. But proving never is hard. Eventually the question became, is there any x at all, however large, at which 1 mod 4 primes catch up to 3 mod 4? In 1914, the British mathematician John Edensor Littlewood proved a result that should have raised eyebrows. He showed that the difference between the actual count of primes up to x and the smooth function approximating it changes sign infinitely often. The two counts oscillate around each other forever. This wasn't a direct attack on Chebyshev's conjecture, but it had the same flavor. It said, persistent biases in the prime distribution have to eventually break. Sign changes must happen. So mathematicians turned to the 4 mod 4 race. If Littlewood's logic applied here too, then somewhere there had to be a first x at which 1 mod 4 primes catch up. The trouble was, where? The first place that 1 mod 4 could possibly catch up had to be enormous. Hand calculation could only reach so far. By 1930, computations had been pushed to a few thousand. Still no catch-up. By 1940, the search reached the tens of thousands. Still nothing. 3 mod 4 leading at every step. The conjecture was holding. If Chebyshev was right, no catch-up would ever happen and the conjecture would be proven by some clever argument. If Chebyshev was wrong, the first catch-up would appear somewhere and someone would find it. The race was on between the conjecture and the computers. By 1950, the search had pushed past 10,000. Still no catch-up. The numerical evidence kept reinforcing Chebyshev. A century of data and 1 mod 4 had never won. Not even once. It started to feel like maybe Chebyshev had been right all along. In 1957, a British mathematician named John Leech finally pushed the search past 26,000. He ran the count, prime by prime, comparing the two residue classes. The 3 mod 4 lead held 20,000, 25,000, 26,000. The lead was small now, only a handful of primes, but still positive. Then at x equal to 26,861, it happened. The count of 1 mod 4 primes up to 26,861 is 1473. The count of 3 mod 4 primes up to 26,861 is 1472. 1 mod 4 leads by exactly 1. After 104 years, Chebyshev's conjecture was disproven. The lead didn't hold. The very next prime, 26863, is 3 mod 4, and 3 mod 4 took the lead right back. The crossover at 26,861 was a 1 prime crack, lasting for a single integer's worth of x before sealing back over. But the crack was real. It meant there could be more. 5 years later, in 1962, two Polish mathematicians named Stanisław Knapowski and Pal Turan proved a stronger statement. There are infinitely many such crossovers, in both directions. 1 mod 4 catches up infinitely often. Then 3 mod 4 catches back up infinitely often, forever. The race is not won. It is a sustained, oscillating contest. 3 mod 4 wins most of the time, but 1 mod 4 has its moments, infinitely many of them, scattered out into the universe of large numbers. For 30 years after Knapowski and Turan, the question was, how often does 3 mod 4 lead? If the race is oscillating, with both sides catching up infinitely often, then how dominant is the bias really? Is it 60% of the time? 70? 99? The answer came in 1994. Two mathematicians at Princeton, Michael Rubinstein and Peter Sarnak, published a paper in the journal Experimental Mathematics. The paper was titled simply Chebyshev's Bias. Their result, assuming the generalized Riemann hypothesis and a technical condition about the independence of the zeros of certain L functions, was a precise number. The logarithmic density of x, for which 3 mod 4 primes lead 1 mod 4 primes, is approximately 0.9959, 99.59%. That's the long-run fraction of the x-axis where the 3 mod 4 side is winning. Almost all of it. Out of every 10,000 checks, the 3 mod 4 primes are ahead on 9,959 of them. The 1 mod 4 primes get their nose ahead only on the remaining 41. And the same kind of analysis works for other moduli, primes modulo 3. There's a similar race between 2 mod 3 and 1 mod 3, with 2 mod 3 winning. Primes modulo 10 between those ending in 3 or 7 and those ending in 1 or 9, 3 and 7 win. Primes modulo any number. There's always a bias. There's always a winning side. The percentages differ, but the phenomenon is universal. So the bias is real, persistent, quantifiable, and present in every modulus. We have not yet said where it comes from. Here is the reveal. The bias has nothing to do with anything mysterious about primes themselves. It has to do with prime powers. Take any odd prime, square it. What residue does the square fall into modulo 4? If the prime is 1 mod 4, its square is 1 squared equals 1 mod 4. If the prime is 3 mod 4, its square is 3 squared equals 9, which is 1 mod 4. Either way, the square is 1 mod 4. Every odd prime squared lands in residue 1 mod 4. Always. Without exception. What about cubes? An odd prime cubed equals the prime times its square, so cubed equals prime times 1 equals the prime itself, mod 4. Cubes stay in the original residue. Fourth powers? Fourth power equals square of the square equals 1 squared equals 1. Fifth powers? Back to the original residue. The pattern, even powers of any odd prime, all live in residue 1 mod 4. Odd powers stay in the original residue. So the residue class 1 mod 4 is collecting two things. The primes themselves that happen to be 1 mod 4, and the squares, fourth powers, sixth powers, of all odd primes. Both classes contribute prime power weight to 1 mod 4. The residue class 3 mod 4 is collecting only the primes themselves that are 3 mod 4. No squares, no even powers, nothing extra. The natural counting function that mathematicians use here is not the number of primes. It's the sum of logarithms of prime powers, weighted by inclusion in each residue. And for that counting function, the residue class 1 mod 4 runs ahead because it's collecting the extra mass from the squares. The extra mass is on the order of the square root of x, small compared to the main term, but persistent and positive. To compensate, when you count just the primes themselves, without the prime powers, the 1 mod 4 primes have to come up short by exactly that square root of x amount in order for the total weighted counts to remain asymptotically equal. That's the bias. 3 mod 4 leads by approximately the square root of x divided by the logarithm of x forever, because the residue class 1 mod 4 is secretly hosting all the prime squares and the books have to balance. The exact same logic explains every other modulus. Quadratic residue classes host prime squares. Quadratic non-residue classes don't. So the non-residue classes lead the race in every modulus, always. The bias is not random, it is not a coincidence. It is a forced consequence of the fact that squaring a number lands you in the residue class 1. Chebyshev saw the bias in 1853, but never knew why. Leech disproved the absolute version in 1957. Rubinstein and Sarnak quantified it in 1994. The reason, when you finally see it, is the most natural arithmetic fact in the world. Every square is 1 mod 4. The same logic, run modulo 3. Every prime, when squared, lands in residue 1 mod 3. The class 2 mod 3 never collects any prime squares. So 1 mod 3 gets the hidden boost from prime powers, and to keep the natural counts balanced, the primes themselves come up short in 1 mod 3. 2 mod 3 wins the race. The bias is forced by exactly the same mechanism. Run it for any modulus q. The quadratic residue classes mod q always host the prime squares. They always get the hidden boost. They always come up short on primes. The non-residue classes always lead. That's the entire phenomenon. A century and a half of mathematicians chasing a numerical pattern, finally explained by the deceptively simple observation that the square of any integer is always a quadratic residue. The bias was hiding in the definition of squaring itself.